Okay, so welcome to the webinar today. We're going to be talking about building microservices with the 12-factor app pattern on AWS. I'm Abby Fuller. I work in developer relations for AWS, which is a fancy way of saying that I'm still just a regular developer, and instead I go around talking to folks like you. So at conferences and workshops and demos and webinars just like this one. So we only have a couple minutes today, so we'll get started. The way that we're going to look at it today is our 12-factor app principles plus our microservices principles are what can lead you all to really great and scalable architectures. So starting with the 12-factor application, these are the 12 kind of pieces to success that we can use in order to have a really great and scalable application. So it doesn't matter what language you're writing in or what tools you're using, but if you think about all these principles from the beginning, you can build something that's really great and also really resilient. So the first step here is your code, and our principle here is one code base tracked and revision control with many deploys. So in this case, our version control is Git. That's a really popular one. The tool that you're using for Git can range from anything to AWS's code deploy and code build and code commit to GitHub Online. So the way that a local developer does this is I work locally in my IDE. I commit through Git. And then I have a deployed version that I deploy on my remote servers. So work locally, commit to GitHub or a code commit, and then deploy it to EC2 or Beanstalk or ECS or something like that. The one code base and many deploys ends up looking something like this. So from Git or GitHub, I end up with a number of different revisions. So I might go to a dev environment or a second environment or a QA environment or a production environment. But it's all the same code base tracked in the same central location. So I can do different versions and different revisions for my different environments, but it's all tracked in one place. And that lets me walk through the progress of my application. So from a local commit to a testing commit to a final QA commit, and then at the end to what I have deployed in production. The next step for us is dependencies. So with dependencies, you want to explicitly declare and isolate them. So if you have a function that's needed by multiple pieces of code, it should be packaged into its own library and then included inside your deployment package. So if you have to include a special library or binary, that should be wrapped up and packaged in the same bundle along with your code. Here's an example of what that might look like in Node.js. You use the package.json, and you can install them with npm install. But that package.json is included along with the rest of your code. So when you go out, when you deploy your application, all of its dependencies are declared right there. Here's an example of that in Python. So you use the requirements.txt file. You can install that with pip install, and the same principle. Everything that you need to run your application is included inside so that it gets deployed at the same time as the rest of your code does. Here's another example. It's with Ruby. You declare that in the gem file. You would run that with bundle install. What's also important here, though, is dependency isolation. So you never want to depend on the host to have that dependency. So in this case, it means that I don't want to rely on my EC2 instance to have that dependency. I want to rely on that code itself, which means that I should package it up with the code itself. So I use my bundle install or my gem install, or my pip install or my npm install. But I want to install those requirements as part of the code and not assume that they'll be there as part of the host. Another way that has really been common of doing this recently is Docker. So as part of my Docker container, I can install all my dependencies, my code, and my binary, and they get wrapped up inside the Docker container. So that container has everything that it needs to run both locally and then on a staging environment and then a production environment. I can declare them in a different way in my Docker file. So I start from my base image, I run apk add, which is installing some packages for me. I choose a directory, and then at the end, I can build this whole container. So my Docker file is my set of instructions. I can build it with Docker build, and then that little box has everything that it needs. So it's code, it's dependencies, it's packages, and I can declare those, build it, and then I can deploy that container to any of my hosts. Docker run runs the contents of that container. So I can run it the same way, whether it's on development or production or staging or QA. But since it has all of its dependencies and also its code, all I need to do is Docker run. The second piece for this is the config, and I want to store that as part of the environment. So depending on the service that I use, I can set that configuration using the environment in which the service runs. So that might mean I include an environment variable, or it might mean that I look up an environment variable based on the environment that I'm running in. So I look up that a database key is different for my development environment versus my production environment. And I can pass that configuration along as part of the package as well. So saying where I should look for an API key or for a token or for a variable, I can pass that along as part of the container. So when I deploy it, it just picks up the correct value based on the environment that it ends up running in. So development versus production. However, that's not necessarily the best way to do it. So if we're looking at kind of the right way to do it, what we should do is we should have the exact same container that I can deploy to both environments. So my configuration is then part of the environment on the host. So same container goes to both development and production, but the configuration itself is part of the host. And I think that's actually the opposite to what I just told you to do for dependencies, right? So dependencies should be included as part of the container themselves, as part of the application themselves. But the configuration is not quite the same. So instead of keeping those secrets inside of the container, which I commit to version control or Docker Hub, I keep those as part of the host itself. So that means that my container, it gets deployed to my different hosts. I start to run it. So for example, with Docker build and then Docker run. And then it picks up the configuration from the environment that it's running in. So it might pull a database and a secret, but then my environment ends up being customized when I'm actually running the container. So Docker run, I pass it the string of my database, and then it picks up the secret and the actual database name from the process that's running on the host. All applications have backing services as well. So that would be like a database or a cache. And our best practice here is to treat local services just like remote third-party ones. So don't connect directly to it, but address it like you would to any other kind of third-party resource. So use a CNAME, which gets you flexibility and reconfigurability. So I pass in the CNAME for my database, and even if it happens to be a local database, I treat it just like I would a remote database. And that actually works really well, right, with our pattern, because if I work locally and I can pick up a local database, but I still address it like I would a remote database, it lets me use that same pattern from local to development to production, because I'm addressing all of my resources the same way, regardless of whether they're local or remote. And that means that I can use our correct pattern, which is being able to deploy that same container regardless of whether it's development or production or local. Once you've kind of built and you've included all of your dependencies and code and packages, you've talked about how to address remote databases. We get to our next step, which is how do I build, release, and run my application? So with build, I have my dependencies, I have my code, I have my binaries. They all end up in that same package, which for us is our Docker container, but it could be anything else, right? It doesn't have to be inside a Docker container. That's just one way of doing it. But I have all my pieces. They're all located together. That build artifact plus the configuration is what ends up being my release. So that build artifact in this case is my Docker container. So that's what gets deployed to my development host or my production host. We've talked about the config, which I pick up from the environment in which that build artifact is running. And that those two things together equal my release. So an example with ECS, so the Amazon Elastic Container Service, I pass in my image, which is my Docker build artifact. The config is addressed in the environment, and that's where it says, this is the name and value of the environment variables that you should be looking for. Here's where to find them. But that depends, again, on the environment in which that container is running. So this task definition, which describes how to run my Docker container, basically tells ECS, here's where to find all of these pieces that we need that equal my release. So my Docker container, which is my build artifact, and then my config, which I can pick up once the container is deployed. So what it looks like running is it ends up with a task definition, and it has a release number associated with it. In our case, it's version 1. And then I have a second release, which is version 1.0.1. And then once they're deployed, that's what my revision ends up being. So I start off with 1.0.0, And then once I deploy a second, I go to 1.0.1, which means that I can do both minor and major version upgrades. So maybe a minor upgrade just has a little change, and then a major upgrade has a large change. But when you walk at all those pieces back, I have not only the release number, but I also have the task definition and what changed in that task definition, which I can map back to where the container changed and where the content of the container changed. So I can track my one deploy all the way from my local build process to my CI/CD build process to my final deploy. So it makes it a lot easier to debug and see what's going on in production as well, because I can map all those things back one-to-one. Then we're looking at stateless processes. So a stateful container will store its state in a local disk or local memory, which means that your workload ends up tied to a specific host that has that state data on it. So a stateful data might mean like an action that someone's taken is stored in local memory instead of on a remote database. We don't want to do that, because when you look at how kind of hosts have started working with Docker containers or with stateless infrastructure, you don't know that you're always going to have the same host, right? Because hosts, especially in an ECS cluster, I auto scale them up, I auto scale them down, and I don't want my workload to be tied to any specific host. So instead, I store my state in somewhere that's designed to store that state. So that might be a cache or a database. I work in my container. If my container needs to store state, it sends it to that database or that cache, which I can address through a CNAME like I would for any other remote resources, instead of storing it in local memory. So that means that my state isn't tied to, my workload isn't tied to any specific host, right? The user takes an action, I work, I have everything in the Docker container, it processes what my user is trying to do. That state is stored in a cache or a database, and then I never have to worry about whether that state is there when I need it. So even if the user ends up hitting a second host, I have all that state and it's not tied to one specific host in my infrastructure. The next step is port binding. So that means being able to address services by specific ports. So port 32456. And what this process ends up looking like is I work, I hit my service, and then I hit a service. So /API/users or /API/auth. And that maps to a bunch of ports that are mapped to the service itself. So /API/users is mapped to both 32768 and 32192. And what's nice here is that instead of having to call a specific port, I can call just that group. So instead of having to specify everywhere an exact port binding, I just have to specify that target group, which I can do at the application load balancer level. So if I hit /API/users, I don't have to explicitly say, okay, so I need to hit 32768 and 32192. I can just point to /API/users, and I can let the load balancer handle the rest. Next up is concurrency. So for example, I might have an API, I might have a web, I might have a worker, but I don't usually want to just have one of them. So a best practice here is to build my application in such a way that I can have multiple processes working for the same application. So instead of being limited to, okay, so this runs, and then the next one runs, and then the following one runs, how can I make it so that I have, for example, 4 workers that work off the same queue? If I have a large host, I can run more concurrent processes. If I have a smaller host, I can run fewer concurrent processes. But ultimately, I just want to be able to complete the work a little bit faster. And writing my application in such a way that it allows for multiple processes or workers is what lets me process the work quicker for the end consumer, which is whoever's using my application. Next up is disposability. This ties back to how we spoke about your dependencies needing to be part of your application and how we didn't want to store state on the host itself. So what we want to aim to build here is a fast launch time, a very responsive application, and a graceful shutdown. And these let us account for the fact that we'll have new hosts that are spinning up very quickly. We want to have a graceful shutdown so that if we lose one of our hosts, if we take it down, that our process handles that as well. So instead of just going right to sig kill, send sig term first so that our process is shut down gracefully. Fast launch, you want to minimize the start time of your process. So scale up really quickly in response to traffic spikes. An ability to move to another host if you need to. So if you lose one in an auto-scaling group or you add a new one, and that crash processes get replaced even faster. This is an example of what sig term looks like. So I send sig term and it shuts down everything gracefully. So it wraps up connections instead of just terminating them. And then this lets me handle my scaling up and scaling down a little bit better as well, because instead of just terminating user connections, they shut down gracefully. So something that a lot of you are probably familiar with is the whole, it works on my machine or it works on staging. And we can solve that with something called dev prod parity. And that means that since we're storing everything in version control, and you should remember this picture from a couple of minutes ago, but store everything in version control and I send my different versions out to different environments. And this lets me go for dev prod parity, especially if I'm wrapping everything up in my applications like a Docker container. I can use that same container locally. I can use it on remote on a staging or a production server. And that means that everything stays the same or very close to the same. So I get a lot less of the situations where it's, well, it worked on my machine, or, well, it works on staging, or it works on production. Since you're using the same code, the same application, all wrapped up in the same package, I can use that same package in all my different environments. And that lets me keep those environments as close to each other as possible. Next up, we have logs. So what you should be looking for here is treating logs as an event stream. So keep the logic for routing and processing logs separate from the application itself. This lets you do a couple things, right? So most importantly, it lets you get logs about an application even once the application has died, right? Because a lot of us in the past have had a situation where I started off my process or I started off my application and it died really quickly because something was wrong. And since my logging was tied to the application itself, once it died, I didn't have any logs because the logic for processing those logs was part of the application. So keep them separate. So keep my application log, my application code, and my logging library separate, and then I send them to a separate location. So in this example, it's Elasticsearch. But you'll see that in this example, the application code and the logging library are together as part of the same process. So that means that if my application doesn't start up properly, or if they haven't fully flushed out, some of my logs get lost. So what I can do that's correct is I can run my application code as one process and my logging agent as a second process. So my logs go to an agent, which then is responsible for exporting them off the host. So that means that regardless of what's happening in my application, it's always sending its logs, and then that process itself, which might have crashed, and that's why I'm getting logs, isn't responsible for sending those logs to the third location. The logging agent is, so it can handle exporting them even when my application code is no longer running. I can also have containerized code that writes to std out. That means that Docker connects my container's standard output to a log driver. You can have a couple different log drivers in Docker. So an example here is either FluentD or AWS logs. There's lots of different choices here. And I think the best probably answer is this last one, right? So my container, it writes its code to the output, and then the output goes straight to a logging driver. So I'm not responsible for keeping a process up. I can just ship them off straight to another location. So in the AWS logs case, it'll go to CloudWatch. So just by doing Docker run, which runs my container, it will ship everything off to CloudWatch. Next up, we have admin processes. So you're always going to have some of these, right? So they're kind of inevitable. So an example of this might be migrating a database or fixing broken data or sending a report to someone. Those are always going to happen. And you should run those processes just like any other process. So it's really easy to fall into the pattern of, well, someone just goes to the server once a week and pulls this data and emails it to someone. But you should run these processes just like any other process. So either containerize them or make them start up and scale quickly, respond gracefully to shutdown. You should run them the same way that you would anything else. And then you avoid the whole problem of, well, it doesn't work here anymore, or actually this doesn't work on this host. So run them like anything else, use workers, use processes, make sure that they have all their dependencies in their configuration. So next up, we have componentization. So that means breaking everything out into its actual separate pieces. So each component is a 12-factor application. So I have my code base, my dependencies, my configuration, my port binding, my statelessness, my fast launch time, my graceful stop, my logging stream, and my concurrency. With my microservices, I want to organize them around capabilities. So that means, what is my platform actually doing? What is the job that all of my services are doing? And each major capability of that platform becomes a component that has its own 12-factor application. So every single job that I'm doing, so a UI service or an ordering service or a web service or an API service, each of those jobs, each of those capabilities are their own component that should have its own 12-factor application. So they should all follow those principles that we just talked about. So the code base, the dependencies, the log stream, the concurrency. So next up, we have decentralized governance. And what that means is that so each process should be using its own persistence layer, but sharing it when it needs to. So a better example of this is that I have a game client. It's written in C++. It uses a game server, which is Java. It stores its data to Redis. But I also have a user accounts backend, which is also in Java. And both my game client and my website can both read from that user accounts backend. So they don't share persistence when they don't need to share persistence, but they have access to the same things only when they need to. So my website might be using a React renderer and a microtransactions database, both for its backend, but it can also look at user accounts. My blog might only be able to look at my WordPress backend and then store its data in SQL. So I have separate stores of persistence, and things share access to backends when they need to. But it's all decentralized. So I'm not all relying on one database where everything can read and write from. They all store their state where they need to in separate persistence layers, but they share access to backends where they need to with something like user accounts database. The way this works to maintain is that I start off with my engineering team, right? They write their code, automation deploys the code. I have monitoring, which might catch something bad if it happens in production, which triggers an alert, which in turn pages the software engineers that are on call that fix the problem. It's always a different subset of the engineering team that is on call that helps prevent burnout, but that's the cycle that it goes to build and maintain these processes. And that's also decentralized, right? Because I have my automation, which is working on the deployment. I have alerts, which are handled by automatic monitoring, and I have software engineers that are on call. So they're all separate pieces that are all working together to both maintain this code base and also to make sure that there's always someone different on call, which is also decentralized, so that it's not always one person that's building and deploying and monitoring and being on call. It's always a different subset, and we rotate through. With microservices, I want products and not projects, which is a little bit more colloquially referred to as cattle, not pets. But my products grow over time, right? And with microservices, they're part of an ecosystem of connected products that can be at different stages of growth. And I want to treat all of those differently and accordingly. So I don't want to just create throwaway microservices that become unmaintained and then break my ecosystem. I want to keep building these and I want to keep growing them. So they're all a little bit connected, but I want to make sure that everything is maintained and that it all becomes part of that same ecosystem. So don't just create something that I'm going to end up trashing down the road. I can replace it and grow it and maintain it if I need it, but don't just create throwaway microservices that will just not become maintained and will break my nice ecosystem. So with microservices, I want smart endpoints and dumb pipes. So what I don't want is a central bus for communication, because that ends up with performance bottlenecks and it makes me struggle a little bit with feature development. What I do want is decentralization. So different processes use different event streams, they use different event buses, but I have to decentralize that again instead of relying on the same one, and that eliminates bottlenecks. So for example, I have user signup. I have a user that hits the signup API, which makes a couple different calls, both to a user metadata service and a password service. And then asynchronously, I have an email verification service and a friend discovery service. So neither of those second two, that email verification and friend discovery, are necessary for my original signup, right? They don't have to happen immediately. But what does need to happen immediately is my user metadata and my password. So instead, I do those first synchronously, and then I have my email verification and friend discovery that are asynchronously that happen separately that can then broadcast their results back to the signup API and then back to the user. I have event producers. They produce topics, and then consumers can subscribe to a queue, which subscribes to that topic, right? So instead of just feeding the information directly, everything produces events, and then consumers can subscribe to those topics and queues, which can subscribe to the topics that are coming from those event producers. There's an Amazon managed service for microservice communication, which ends up being Amazon SNS, so simple notification service, Amazon SQS, which is simple queue service, and Amazon MQ, which is a managed message broker service for Apache ActiveMQ. Next up, we want infrastructure automation. So in this case, it means automating our container build process. So I work locally, I commit to Git, it's picked up by code build in Jenkins, and then that's what results in my final built Docker container. So you'll notice that we're not building our Docker containers by hand. We're letting an automated process do that, which means that it's more repeatable, it's more scalable, and it's less inclined to make mistakes because I write that same build process, and that's always responsible for building my containers the exact same way. I also want to automate the provisioning of the services that host my microservices. So in this case, it's our containers. An example of that is Terraform or Ansible or CloudFormation from Amazon. So that's responsible for making sure that all of the servers that my application or my containers run on, they all look the same. So it's not a special Snowflake server that I had to SSH into to install a new package every time. It's automated and repeatable. And then finally, I want to automate the placement of my actual processes onto those hosts. So with containers, that's a container orchestration tool. So how do I deploy, manage, and scale my containerized processes? So I could use something like Amazon ECS, or I could use Kubernetes, or I could use Docker Swarm. There's a ton more examples out there. So the way this looks all together is I have a developer, they're working locally, they push to a version control repository. I have my test and deployment manager, and that has two different paths. It has an image build service, which then pushes to a container image repository. So in this case, maybe we'd be using Amazon ECR. And then I have my infrastructure provisioning, which provisions the services, the servers that my services are running on. So in this case, that would be the EC2 instances that make up our ECS cluster. And then I have my container scheduling and orchestration, which pulls images from my container repository, so ECR, and that places those containers on the EC2 instances that were provisioned by my infrastructure provisioning tool. With a more specific example, I have developers that push to code commit, which then pushes to code pipeline. And then I have my two paths. I have my image build path, which is code build, which pushes to ECR. And then I have my infrastructure provisioning, which uses CloudFormation. And then I have Amazon ECS, which is responsible for both pulling images from ECR and then managing, scaling, and deploying my containers to the infrastructure that was provisioned via CloudFormation. A non-Amazon example here would be I have developers pushing to GitHub, which then kicks off a build in Jenkins, which then builds and pushes an image to another container image repository. So we'll use Docker Hub. My infrastructure provisioning path is via Terraform, and then my scheduling and orchestration of my containers is managed with Kubernetes. So in summary, we have some 12-factor application principles. So my code base, my dependencies, my configuration, port binding, statelessness, fast launch time, a graceful stop process, a log stream, and concurrency. And then on top of that, I have my microservices principles. So automation, componentization, it's product focused, and it's decentralized. And all of those things together are what can allow you to build really resilient and scalable applications. So thank you. If you have any questions, you can reach me via email. So it's abbyfull@amazon.com. You can reach me on Twitter. It's @abbyfuller, or you can find some of my work on GitHub. And now we have a few minutes for questions.